The design, test, and evaluation of a fast reactor power plant is part of the United States Atomic Energy Commission's Power Reactor Program. Argonne National Laboratory, having pioneered in fast power reactor work, is engaged in an extensive effort in the fast reactor field. The experimental Breeder Reactor 2 complex is being developed to appraise its operation and performance in nuclear power production, a direct step in achieving an economically feasible large-scale plant. This facility will consist of an unmoderated breeder reactor with the complete primary reactor circuit submersed in the sodium coolant. Performance specifications include the production of 62.5 megawatts of heat and 20 megawatts of electricity. The inclusion of fuel fabrication and spent fuel processing will establish the EBR-2 as the first completely integrated power reactor system operating on a closed fuel cycle. Research and development for this integrated system involves the coordinated efforts of many of the laboratory's scientific divisions. The Idaho Division, located at the National Reactor Testing Station, operates the experimental Breeder Reactor 1. Experience gained since 1951 in the operation of this reactor forms the foundation for fast power reactor development. This is the first reactor to employ sodium-potassium alloy as a coolant and to utilize the direct current electromagnetic pump. During this time, the reactor performed satisfactorily as a steady power source, demonstrated the breeding concept, generated the world's first electricity from nuclear power, and served its primary function in providing fundamental fast reactor information. When EBR-1 was operated at power-to-flow ratios 1.5 times the design ratio, some undesirable dynamic characteristics were observed. These were a prompt positive temperature coefficient and a tendency toward spontaneous oscillation of power. It was believed these characteristics were related and that the cause of the prompt positive temperature coefficient was either the Doppler effect, which increases the effective fissioning cross-section due to heating enriched uranium, or to mechanical motion of the fuel elements. Enriched uranium in the form of a helix was prepared for measurement of the Doppler effect in fast reactors. This experiment was performed in the laboratory's critical assembly facility, ZPR-3. The helical form was adopted to minimize motion due to heating, which could produce undesirable side reactivity effects. Positioned within an assembled EBR-1 core mock-up, the helix was periodically heated, then cooled on a 20-second cycle time. Careful measurement of the power oscillations resulting from the cycling made it fairly certain the Doppler effect was much too small to have been the primary cause of the prompt temperature coefficient observed in the reactor. Concluding that the primary problem was mechanical motion, it was decided to investigate EBR-1 performance as part of an overall program to study reactor dynamics. A rigid core assembly to restrict mechanical motion was designed for EBR-1. Designated Mark III, the core structure consisting of laminated steel discs was machined and assembled by the laboratory's central shops. The inside hexagonal surface fits the outer perimeter of the blanket subassemblies. These discs are held and aligned with tie rods. Paralleling the assembly of the core structure, fabrication of Mark III fuel was underway by the Metallurgy Division. The fuel for the Mark III core is uranium enriched to 93%. The blanket is normal uranium. Both blanket and core uranium are alloyed with 2-weight % zirconium. Clad with zircaloy 2, they are co-extruded into the form of a rod. The rough cores for the blanket extrusion billets are produced by casting in a multi-cavity graphite mold. The enriched uranium is melted in a 5-kilogram batch and cast in a single-cavity mold. A graphite crucible coated with ceramic wash is charged with the uranium biscuit and zirconium sponge for the blanket alloy. Melting and alloying is done by induction heating in a vacuum of 10 microns or less. After alloying, the metal is bottom poured into the mold by lifting a stopper rod. These castings, after machining, are tested for homogeneity by a non-destructive method. A sound transmission principle is utilized. 5 megacycle ultrasonic waves are generated by means of a quartz transducer and sent through the metal. The quality of the casting is graphically recorded on a strip of electrosensitive paper. The casting, after further machining, yields 2 extrusion billet cores. These cores, assembled with copper-nickel end plugs, are encased in a sleeve of zircaloy 2. A copper jacket is added to prevent contamination of the billet components during heating and to provide lubrication during extrusion. Closed by heliarc welding, the assembled billet is then evacuated, outgassed, and sealed. The billets are co-extruded by nuclear metals incorporated to rods of 1/2 inch diameter. Upon return, they are inspected, pickled to remove the copper, and swaged to a specified diameter. Heat treated for stabilization, the rods are cut to appropriate fuel and blanket lengths, and the cladding thickness measured. To join the sections of either type rod, a commercial glass lathe was specifically adapted at Argonne for tungsten arc butt welding. This welding operation is extremely precise because of the difficulty of fusing the high melting zircaloy without excessive melting of the uranium. A 10 mil zirconium spacer disc separates the enriched and blanket sections on each fuel rod. Chill and gas retainers surround the electrode and weld area. Welding is purposely limited to the 20 mil zircaloy cladding and is made in a double pass, each pass requiring a different welding current. A section bond is made at each weld by fusing the metal in a small zone to add mechanical strength. The cladding is protected against oxidation by passing a stream of helium through the Vicor tube. After heat treatment, cladding thickness is measured by an eddy current method. Eddy currents are induced in the zircaloy cladding by means of a point probe. The apparent impedance of the probe is influenced by the cladding thickness. The bond on the rods is then scanned by the ultrasonic transmission technique. Non-destructive testing methods help to ensure the quality of the completed fuel and blanket rods. Zirconium ribs are spot welded to rods ground to their finished diameter. These will provide accurate spacing of the tightly clustered rods in their final geometry. The welding operation is performed automatically on a specially designed condenser discharge type spot welder. Welds are placed at 1/4 inch intervals along each of the 3 ribs, a total of 240 welds per rod. Machining operations complete the fuel and blanket rod fabrication. The completed core structure, ready for installation in the reactor tank, has a total height of 9 feet and 5 inches. The reduced diameter at the bottom will receive the core and inner blanket rods. The structure rests on this shoulder, with the inlet plenum chamber located just above the upper blanket. This plenum chamber contains 4 two-way inlet valves for switching from series to parallel flow. The up position of the valves permits series flow through the inner blanket and core, while the down position allows parallel flow. The plate above the inlet plenum chamber has seal rings to prevent bypass leakage between the inlet and outlet plenum chambers. This seal plate also contains 2 flow control valves for throttling the exit flow from the inner blanket under parallel flow conditions. Under series flow conditions, these valves are closed. Additional rigidity is obtained by an arrangement of clamps around fuel and blanket subassemblies at the core center line and at the seal plate. The upper part of the structure is primarily shielding with an overflow plenum chamber near the top. The top plate holds the actuators and position indicators for the various valves and clamps in the structure. The core structure is installed in the same reactor tank that housed the EBR-1, Mark I, and Mark II cores. Fuel and blanket rods, with their attached extensions for handling, are positioned within a hexagonal can. Complete subassemblies within the hex can contain 36 rods, and depending upon location within the structure, will consist of fuel and/or blanket material. A tightening rod is located at the center of each subassembly, and, when expanded, provides additional rigidity. The thorough temperature instrumentation of Mark III includes thermocouples in the plenum chamber structure, fuel rods, blanket rods, and coolant passages. The complete Mark III loading contains 19 subassemblies. 7 enriched subassemblies comprise the core. These are surrounded by a ring of 12 inner blanket subassemblies. Criticality was achieved on November 11, 1957. It was determined to be 47 4/10 kilograms of uranium-235, within 2% of the critical mass determined from the mock-up of the core on the Zero Power Reactor 3. Operating test data indicates that Mark III would be stable at several times design power, and the instability apparent in Mark II was due to mechanical design and is not inherent in fast reactors. Adjacent to the EBR-1 building of the laboratory's Idaho division is the Zero Power Reactor 3. This critical facility was placed in operation October 20th, 1955, one of a family of critical facilities preceded by ZPR-1 for the Nautilus reactor and ZPR-2 for the Savannah River reactors. ZPR-3 is an extremely flexible machine for investigating fast reactor physics, providing a proof test of the physics of a particular design and a range of experimental information to improve the accuracies of calculations. In fast reactors, the mean free path of neutrons is in the order of centimeters. Hence, a reactor made up of components of thickness equal to a fraction of a centimeter essentially looks like a homogeneous reactor to the fast neutron. Basically, the Zero Power Reactor is a machine of 2 halves in which fissionable material can be assembled. Each half is a square matrix of 961 numbered tubes. Previous experiments have determined those quantities of core material that may be safely loaded in each half. These quantities are dependent upon the dilution with other materials and the ratio of enriched uranium to depleted uranium. Since operation of ZPR-3 began, more than 30 critical assemblies have been studied, ranging in critical mass from 46 to 221 kilograms of uranium-235, and varying in composition, size, and shape. Loaded according to the experimental program, these halves are then driven together to form a critical assembly. No coolant is provided. Consequently, this reactor must be operated at low power. Determination of critical mass, flux distribution, control rod worth, and core arrangements has provided a whole range of experimental facts for application in any fast reactor system. In the present fast reactor program, the ZPR-3 is being applied to the study of the nuclear aspects of the experimental Breeder Reactor 2 engineering design. The configuration and composition, as specified by the designers for EBR-2, is an enriched core having a height of 14 22/100 inches and a diameter of approximately 19 inches. The core contains 14 modified fuel subassemblies, which are utilized as control and safety rods. The enriched core is surrounded by a blanket having an outer diameter of approximately 61 inches and a height of 58 1/2 inches. These dimensions are then translated into a loading configuration for full-scale mock-up in the critical facility. Core, control rod, and blanket regions are laid out in composition and dimensional details within drawers and fractions of drawers. These plans are then applied to the individual drawer loading diagrams. After final approval of the loading pattern, these diagrams are utilized as a guide in the loading of each drawer. The highly enriched uranium-235 in the form of 1/8 inch thick plates is color-coded red to distinguish it from the depleted uranium, which is black. Only 2 drawers may be loaded at any one time on the loading table. Since the distribution of materials in a drawer has a pronounced effect on reactivity, the desired arrangement must be maintained. The drawers are loaded according to their corresponding drawer masters, with uranium as the fissionable material, stainless steel as the structural and cladding material, and low-density aluminum to represent the sodium coolant. Aluminum has been selected to represent sodium because of its similarity in cross-section for fast neutrons. To confirm the equivalence between aluminum and sodium to be used in the EBR-2, it is necessary to substitute containers filled with sodium. This same experimental procedure is used to determine the reactivity effect of the fission products which will be present in the EBR-2 fuel. As the drawers are completed, they are checked, then transferred to the adjacent shielded room. Loading of the 2 halves proceeds simultaneously until the mock-up is complete. Five empty channels in each half indicate the position of withdrawn control drawers of the critical assembly. The central enriched uranium core, the mocked-up EBR-2 control rods, and surrounding depleted uranium blanket have now been arranged according to engineering design. The blanket region immediately adjacent to the core has been loaded in drawers, while the blanket region outside this immediate area is of more coarse structure, although maintaining the same composition. Mock-up is complete, and preparations are made for final remote assembly of the 2 subcritical halves. Oilers and air pressure are checked, and the assembly room is cleared of personnel. The operator activates the scram interlocks, neutron source drive mechanisms, and begins to move the halves together. The reactor is assembled at a rate of 30 inches per minute until the separation is 18 inches. At the same time, 4 safety rods in each half are inserted. These 8 rods must be fully inserted before the separation can become less than 18 inches. 1 rod in each half is a control rod and is left withdrawn until the halves have been completely closed. As the separation of the halves decreases from 18 inches to 3 inches, the speed is reduced to 6 inches per minute, and the final closing is at a rate of 1/2 inch per minute. The slow speed of assembly is fundamental to the safe operation of this machine. With the halves together, the control rods are inserted until at some rod position criticality is achieved. In comparison to reactors designed to remove neutron absorbers to produce a self-sustaining chain reaction, ZPR3 adds either fuel or reflector material. This method of control will also be used in EBR2. Though subcritical, the power level is due to multiplication of the source. When the level is high enough to assure criticality, the source is removed. The reactor is now critical. After criticality is reached, a constant power level can be maintained. The position of this calibrated control rod is used for the determination of the critical mass of this mock-up. Confirming information is determined by moving the remaining portion of the rod into the reactor. The reactor is now supercritical and will increase in power exponentially. Rate of rise in power thus recorded is a measure of the excess reactivity of the assembly. After obtaining sufficient information, a scheduled manual scram is initiated by the operator. The control rods are ejected from the assembly under air pressure, and the halves are automatically driven apart. These occasional scrams are intended to check the performance of the safety devices. Normal shutdown is accomplished by withdrawing the rods at slow speed. The critical mass of this mock-up was 161 kilograms of uranium-235. Additional ZPR3 experimental information allows adjustments of the observed critical mass for slight changes in composition, burn-up, fission product poisons, type of control rod chosen, temperature effects, and sodium for aluminum equivalents. The completion of this portion of the Fast Reactor Program will define the nuclear characteristics of a uranium-235 core. Subsequent experimental programs will investigate plutonium fueling for EBR2. The desirability of fueling reactors with plutonium has required investigation into the mechanical and physical properties of plutonium alloys. This facility, designed for complete containment in an inert atmosphere, permits studies of properties and fabrication of plutonium-containing materials with a minimum of hazard. The range of plutonium concentration in alloys studied has been from 10 to 30 weight%. Because the pyrometallurgical process permits control of residual fission products, varying concentrations of 3 to 15 weight% fission product elements have been included in the alloy. The alloy tested is of 70 weight% uranium, 20% plutonium, and 10% fission product elements. Irradiation stability is good, and thermal conductivity is slightly less than uranium. This alloy shows excellent compatibility, even under irradiation with the sodium coolant. The pumping of sodium in a demonstration loop introduces another aspect of EBR2 development. Sodium is chosen as the coolant because of its high thermal conductivity, low vapor pressure, and stability at high temperature. Studies of the EBR2 design have been made with a 1/4 scale model tank containing the primary reactor circuit completely submersed in 5,000 gallons of sodium coolant. The exchange of fuel subassemblies is accomplished by remote handling beneath the sodium in the primary tank. Experience in the handling of fuel components, sodium pumping, and sodium instrumentation has established the safety and feasibility of this submersion concept. Concurrently, full-scale prototype components have been constructed and are under test. Direct comparisons are made of reliability, operating characteristics, system preheating, and cost. 3 basic types of pumps are being tested. A 250,000 ampere direct current homopolar generator and a 10,000 gallon per minute DC electromagnetic pump have been developed by the laboratory. Preliminary operation of this pump has shown overall pumping efficiencies of 20%. A 5,000 gallon per minute vertically mounted single stage centrifugal pump has had more than 6,000 hours of successful operation at 700 degrees Fahrenheit and a 40 psi head. A 5,000 gallon per minute horizontally mounted alternating current linear induction pump has also operated satisfactorily for more than 6,000 hours. The loop is inductively heated by passing 60 cycle current through coils wound over the insulation. Operating at low temperature, this method provides maximum coil life. The infinite flow control feature of the pump makes it particularly applicable for reactor systems. A rotary reactor plug using tin bismuth as the sealant has proved difficult to make absolutely gas-tight. Although sealed when the alloy is molten, further study is required to determine the nature of the small leakage when cold. Sodium piping system components have been developed for flows up to 5,000 gallons per minute and temperatures to 800 degrees Fahrenheit. Parallel to progress in EBR2 physics, reactor design, and system components is the development of the complete fuel cycle. The first phase of the fuel cycle being developed consists of pyrometallurgical reprocessing by melt refining. Since the processed fuel is highly radioactive due to residual fission products and transuranic elements, remote operations are required. Prototype equipment is mocked up in full scale. A 5-foot thick glass shielding window and a 700-pound capacity manipulator are included to study remote viewing and operations. The process sequence begins. The melt refining furnace is enclosed with a bell jar to provide a furnace environment independent of the cell atmosphere. A fume trap to collect volatile fission products is removed. Prior to charging, the fuel pin is mechanically separated from the stainless steel cans and chopped to a pouring length. Due to the self-heating of the radioactive fuel, special containers like the fuel charger must be enclosed and designed for heat dissipation. 10 kilograms of chopped fuel pins are charged to the furnace crucible. The furnace is reassembled. The bell jar confines the gaseous fission products and is sealed to the furnace base by a molten metal freeze seal. High-frequency induction is used to obtain the melting temperature of 1,300 degrees centigrade. After a 3-hour liquation period, the melt is tilt-poured into a mold. The active metal fission products, which have reacted with the oxide crucible, remain behind as a slag. The more noble fission elements remain with the fuel alloy. Continued recycle of the fuel establishes an equilibrium alloy. Radiation damage studies have proven that this alloy is extremely stable. This was